So I think it's time to welcome the second lecture of our winter school today. And so he's Guido De Philippis from New York University, and he will tell us about PDE constraint measures. And maybe at the risk of embarrassing myself a bit, I'll just say a few further words of introduction. So a few years ago, Guido and Philip Rinder, they published an astonishing result, which describes the structure of vector-valued measures which satisfy a PDE constraint. And the proof of this result, well, of this structure theorem was at least partially Fourier analytic, but the theorem itself had many deep, purely geometric consequences. And for example, it immediately solved an old conjecture of Giger in metric geometry, and it also gave a new proof for Alberti's celebrated rank 1 theorem for BV functions. And actually, there are many more applications, and we'll hopefully hear about them later on this course. And for example, Guido and his co-authors have also used the technique to prove exciting new results about rectifiability. And so with that introduction, I think it's time to give the floor to the speaker. So Guido, please go ahead.
Okay, so thank you very much for the kind introduction. And yeah, I think it was a perfect, well, I mean, besides the fact that the result was astonishing, I think it's a perfect introduction to the class. So, well, first of all, let me start thanking for the invitation, for you, Thomas, for taking care of all these things, also with me not responding to all the mails properly. So really thanks a lot. And I really would like to be there in person for several reasons. First of all, because as I was saying, I really like, I'm really looking forward starting again to have in-person interaction with colleagues. I think that mathematics is much better in front of a blackboard, and then because I did my postdoc at the Hausdorff Center in Bonn, so it would have been always nice to be back there. So beside this, what I'm going to talk about is again, I was saying, as Thomas was saying, is about the structure of PDE constraint measures and some applications. And I might start from the applications in a sense to motivate, though it's a bit cheating because some of these applications we discover after after we prove the theorem. So again, let me start. So there are a few somehow. Okay, no. First of all, let me also start with. So a good part of what I'm gonna say, well, at least, yeah, half at least of what I'm gonna say is gonna be in this book here. So this is the lecture notes. So as references. So lecture notes for a CIME class I gave. Course I gave just before pandemic started, basically. So it was Cetraro 2019, and these are collected in this book here. You can also find those online, like on my collected in the book. In particular, you can find some proofs, which you'll probably skip. Okay, so in a sense, okay, so this is like the starting point. So the general question we want to address is what we can tell about the local somehow structure of a measure which is satisfying a PDE constraint. So this would be somehow the the general question I want to address. But before addressing it, so let me start with giving you some example in which this question might be of some relevance. And before giving the example, let me introduce some notation. So that's here on the same ground. So general omega would be an open set of some RD. And I take mu to be a vector valued measure from this omega to some vector space V, which is a finite dimensional vector space. So which you can think to be, and often it will be, some. So obviously we all know that all finite dimensional vector space are isomorphic to some Rn. There will be a norm on this vector space, which again is not going to be much more fancy than the Euclidean norm, but I think that there is some merit in looking at these things like in a, say, a coordinate independent way, in a sense. So there is sometimes there is no canonical identification with Rn, so it might be worth to settle the theory in this way. So so we have given this measure like this. So, and we say that mu is satisfying a differential constraint if so mu. Yes, let's write this way. Let's say it's A free if A of mu is equal to 0, where A is a differential operator which takes, say, function which are C infinity in omega with value in V into function which is C infinity in omega with value in W. Right here is a differential operator of order K. And by this, what I mean is that I can write A. So the action of A over function phi is just the sum of some A alpha D alpha of phi, where A alpha are linear operators from V to W, and D alpha is just the usual. So this is a sum over multi-indexes less or equal than K, and D alpha is just the usual derivative. So this dx d1 alpha 1 dd alpha t. Okay, so and alpha is a multi-index, and the length of alpha is the classical thing. So actually this linear operator maps compactly supported infinity function into compactly supported infinity functions. So by duality you can define it on distributions. So by duality A can be defined on distribution. So that A of mu equals 0, it means that it means that again it would be mu against the transpose of A is equal to 0 for all phi C infinity and compactly supported with value in V star. So A star is just what you would expect. So this is the adjoint operator. Maybe there is a -1 with the alpha here, which is nothing that, so this thing is nothing but, so mu A star phi is nothing but the integral of A star phi, which is a nice smooth function in the mu. Okay, so mu is a vector valued measure. So maybe let me fix also a notation for vector valued measure. So mu is a vector valued measure. So this means that there exists a measure sigma, which I'm gonna call absolute value of mu, which is a positive measure. So let's see this. Usually, they're positive measures, positive radon measure. And the function, which is g, which is usually called d mu over d mu, which goes from omega into v, and this belongs to L infinity of.
Guido, there's a question in the chat that could you maybe write a little bit larger?
Okay, yes. If I do this. So there is this function d mu over d mu, which is called the polar associated to mu. And so basically every vector valued function, every vector valued measure can be decomposed as a infinitesimally, at least, as a direction times some absolute value measures. Okay, so you should think to this as writing a function f as f over modulus of f times modulus of f. Okay, so this is what this decomposition is telling you. And I mean, then the integral against phi d mu is just the integral of phi against so this is, if you want, so phi should something which takes value in the dual of v, or in Rd if you prefer. Okay, so this in principle is the duality v star v. But here again, everything is finite dimensional, so it might look a bit too fancy to not put coordinates, and indeed you might want to put coordinates and nothing is going to change, and I will do it soon, but this is like the framework. Okay, maybe he wants me to try to do this. You prefer this? Okay. So, and here you see the only role played by a norm. That's just, let me say these things, and that's it on this. So the only role played by the norm is in defining L infinity, obviously. But if you change norms on V, these are going to be all equivalent. So L infinity is going to be all the same space. Okay. So in a sense, so okay. The next things, okay, maybe I should have said, so to make these things unique, is that the norm of this polar is going to be 1 almost everywhere, mu almost everywhere. So you see that, okay, if you change the norm, you're basically change. Oops. If you change the norm, you're basically change this polar. Okay, so the norm. The norm is contained into this polar. Or what is not changing, in a sense, is the direction of this. Well, partially. Okay, so the polar should be thought like an infinitesimal direction of the measure. Okay, so the measure is some scalar things, and in each point there is a preferred direction for this measure, which is given by this polar. Okay, so that's the way you might want to think to this decomposition. Okay, so again, so we want to study the structure of this to this A-free measure, but the question is, in the first natural question would be why. So let me give some examples of A-free measures. So the first example is the case of gradient of BV functions. I think most of you know the space BV of omega with values say in Rd. well, so here are some different. Let me call this L. So these are function U, which goes from omega to RL. U is usually an L1 function. And then the distributional derivative of U, and the distributional derivative of U, it's measure, which values in L times D matrices, okay? So this is a spaces which appears a lot in applications, so are again functions of bounded variations. So are those functions for which the distributional derivative is a measure, and this is the right substitute for the first Sobolev space. Okay, so in a sense, we know that L1 is not L1 is not a dual. That's one of the good reasons to start looking at measures, because measures are not really a dual. Okay, so you look to this space, and but then there's the same thing somehow. So by Poincaré lemma, studying this space is the same thing as studying the space of measure mu in value, which are matrix values, such that the curve of this measure is 0, where this one is the row-wise curve. Row-wise. Okay. So this is a matrix, and you want each row to be curve 0. That's the same thing that's saying, I mean, at least locally, that this measure is a gradient of some function, and so studying measures which are curve free is the same thing that studying BV functions. Okay, so the second example, which is probably the one who motivated all of our analysis, is the space of symmetric gradients. Or if you want, BD functions. So this is a space which is quite natural in elasticity and plasticity mostly, which is the space of function U RD, such that when you look not to the gradient, but to the symmetrized gradient, so the gradient plus the transpose, well, this is then a measure in with value in symmetric, with value into symmetric matrices. And again, there is the so-called Saint-Venant compatibility condition. Which tells you the following, so that the space is equivalent to the measure, to the space of measures which value into symmetric matrices, such that I'm gonna call, so I'm not gonna write it, but maybe I can. So such that curl of mu is equal to 0, where curl of mu is a second order operator. So it's not just the curl of the, I mean, sometimes it's the curl of the curl. So in dimension 3, let me give you the precise, well, it's not so interesting, but let me give you anyhow the precise expression of it. So this is something, if you want to look to the coordinates, wait, so we keep the same notation, otherwise mess it up. JH, well, this is gonna be sum over I of DIH mu IJ plus DIJ mu IH minus DJH mu II Okay, but beside the precise expression of its JH, beside the precise expression, what I want to stress is that, okay, so even symmetrized gradient, they can be characterized by being in the kernel of a differential operator. Okay, so so studying symmetrized, studying functions of bounded deformation, so the space of BD is the same thing, the studying measures which satisfy certain differential constraints. And this is more in general, I mean, these things can be abstracted to the situation of elliptic complexes, which again, I don't want to enter too much into, but is the situation in which basically there are, so for which there are two operators. Two differential operators, B and A, such that V is equal, say, let's say mu is equal to B of U if and only if A of mu is equal to 0. Okay, so another example in this sense, which is going to be relevant somehow, is the classical D on K forms. So on differential forms. So the differential on differential forms, for instance, which is a particular case of differential forms. Okay, so we know that the form is exact if and only if it's closed. Basically, besides some global topological issue, which we don't care, everything is going to be locked. Right? So the V is equal to D of mu if and only if. Sorry, mu will be equal to D of V if and only if D mu is equal to 0. Okay, so this is a situation in which it's quite natural to look to measures which are satisfying a differential constraint. So there is another situation which maybe I will have time to discuss. So are there two which I think are relevant for the class? So the next one is about so inner variations of variational problems. So say that you have a map U which minimizes, or more in general, which is a stationary point the integral of f of gradient U with some boundary condition. Okay. Now imagine that, okay, U maybe is something goes from omega to some RD or in general, and that's the situation in which this is particularly relevant. Instead, usually you might have some, maybe M is not. You might have some constraints. You might want to impose some constraint on the image of U. So constraint like U lies in a manifold. So this is a typical situation of harmonic maps in which you minimize the Dirichlet energy among all maps which are manifold valued, or similar situation. So in this case, when you want to compute optimality condition for minimizer, you might not be allowed to move the function into the image. Okay, so the typical thing we do when we want to compute Euler-Lagrange equation is to perturb U by U plus epsilon phi, say. Okay, so typical perturbation is to look to the map epsilon into integral of f of du plus epsilon d phi, and saying that this map has a minimum in 0, and then looking to the derivative of this map, imposing it 0, and getting some optimality condition for you. Okay, but that might be that these things does not belong to sigma anymore. So another type of perturbation which might be relevant is the so-called inner variations, in which you change not the image, but the domain. So this time you map epsilon into the integral of f of d of u composed with phi epsilon, where phi epsilon of x is equal to x plus t times some capital X being a C-infinity compactly supported vector field. So this means that you are basically taking an infinitesimal deformation of your domain and precomposing the map with this infinitesimal deformation, okay? So you're just essentially changing the name of the points. And now, again, this map, so phi epsilon, so phi epsilon is the identity when epsilon is equal to 0. So again, you can differentiate these things for epsilon equal to 0 and get some information. So if you differentiate, so if I call this function, say, g of epsilon, usually what I get is that g prime is equal to 0 if and only if something like this happens, t of u against dx is equal to 0. And since here t of u is what's called the energy stress tensor, so it's f of gradient u times the identity minus okay, let me write this in one dimension because otherwise I'm gonna get, so not in one dimension, but so something we should have this structure here. I wouldn't bet everything on this formula. Anyhow, you get, so this is a d by d matrix, right? So that's what you should get. So this is a d by d matrix, and you see that it has to integrate 0 every time you trace it against a compactly supported, the gradient of a compactly supported vector field. So these things here is equivalent to say that in the sense of distribution, the divergence of the stress tensor is 0, and where this is the row-wise divergence, I think. Okay, so again, being stationary for this problem tells you something about this the stress energy tensor, namely that this is divergence free. Now imagine that, so assume that now you have a sequence uj of minimizers or stationary points such that the energy of uj, so is finite. Well, then usually you expect this energy to have some coercivity, so you can expect uj to converge weakly in some Sobolev space to some mu. Sobolev space. And the next things you know is that T of u, the modulus of T of u is like the modulus of f of du plus gradient f of du times du, which you expect, I mean, for most functions, say power type function, you expect this to be like f of du, okay? So you have the gradient times, I mean, the gradient into something times the same something you expect to be comparable to the function, more or less, unless you're really super exponential in growth. But say for many functions, you expect these things to be true. So this means that T of u is bounded, so T of uj is bounded in L1, so that there exists a measure mu such that T of uj weakly star converge to mu, and the divergence of this measure mu has to be 0, right? Because this was, I mean, it's a linear constraint. So linear constraint passes to the limits through weak convergence. So you end up that the sequence of stress energy tensor is converging to a measure mu, which is still divergence free. And in a sense, mu is encoding the concentration of the energy of the sequences uj, right? Because you see that it's not clear that, so this is a nonlinear expression in the gradient of u, so you cannot pass to the limits unless you have strong convergence. So in a sense, the region, okay, that's a bit cheating though, but the parts where my limiting measure mu does not coincide with the stress energy tensor for the limiting guy, well, in that part, something should happen. So some not strong convergence should happen. And this difference, limiting stress energy tensor minus mu, is somehow encoding the behavior of this non-strong convergence, okay? Okay, so this is my fourth example. Now I give you the fifth example. So maybe, is there any question up to now? Okay. So let me go to the fifth example, and the fifth example is pretty surprising in a sense, and this is related to the converse of Rademacher theorem. So and then probably I won't have time to finish this before the coffee break, but see, so Rademacher theorem say the following. So let's F goes from, let's say, RD into RL, B Lipschitz. Then F is differentiable for LD almost of X. So meaning that for LD almost of X, there exists the f of X, which is a linear function from RD into RL, such that you write f of X plus H as f of X plus dfx apply to H plus little of H, okay? So, okay, so this is a classical theorem in geometric measure theory. So Lipschitz functions are differentiable almost everywhere with respect to the Lebesgue measure. Now the question is, what if I consider another measure mu instead of the Lebesgue measure? So can I find another measure for which Lipschitz functions are differentiable mu almost everywhere? Well, obviously, so can Rademacher holds? Well, obviously, the answer is yes, if mu is absolutely continuous with respect to the Lebesgue measure, right? This is just a question about null sets. The validity or not of Rademacher is just a question about null sets. So every time you have two measures which have the same null sets, Rademacher holds for one, if and only if it holds for the other one. And more in general, if it holds for one measure, it holds for all the measures which have the same null sets. So for all measures which are absolutely continuous with respect to that. Okay, so obviously you can substitute any absolutely continuous measure with respect to the Lebesgue measure, which is not that interesting because basically you're just changing the density. So the question is that really, can I find a singular Rademacher? So can I find a singular measure for which Rademacher theorem holds? So the actual question is this one. So is there a singular measure? Measure for which the Rademacher holds. And this is a series of, I mean, this is step, okay, in a sense, this is just one question of a series of very interesting questions, which is a line of research which has been initiated by, so this fits years long line of research, which I think we can say that was initiated by David Price and Giovanni Alberti. Mariana Chorney, this time I get it correct. David Bates, Thomas as well, and several others. So this has been this fits in a broad framework, which I'm just gonna scratch, but there are a lot of references and cross-references and approaches. So I start apologizing for those who I forget. So can we find a singular measure for which Rademacher theorem holds? This is the question. And in a sense, any such measure, so let me give you a answer. Any such measure should be somehow diffuse in the following sense. So imagine that mu is a delta in a point. Well, then it's easy to construct functions which are not differentiable at mu almost all points, right? You take f of x, take f of x, which is the absolute value of x, is not differentiable at 0. Well, now imagine that mu is the Hausdorff measure restricted, say the k-dimensional, maybe k, say again, L-dimensional Hausdorff measure restricted to some smooth surface sigma. Sigma is L-dimensional surface. So something like this. Well, again, this time you can take f of x to be the distance x from sigma. Well, this is not differentiable along the directions. This is important. Perpendicular to the tangent space of sigma. Right, so you have your function, which is like a cone-like. So this is a cone around the origin. So in this example, and you see that if you approach the origin from different direction, you're gonna get basically different derivatives. Okay, so there is no, so the function is actually, well, I mean, it is directional derivatives, but this do not coincide here. Here is sort of the same. It's just you're just adding somehow a dimension to this example. So everything is nice when you move in the direction tangent to your function, to your surface. But when you move in orthogonal direction to your surface, you see this cone-like behavior, which tells you that the function is not going to be differentiable in those directions. Okay, so that's what's happening here. And so you see that. So these are classical example of measure which a dimension attached to it, and it seems that in this case Rademacher shouldn't hold, because there are always directions along which your function is not differentiable. Okay, so now the question is, okay, so these are somehow good measures. So the natural question would be, is there maybe a horrible looking singular measure which is somehow diffuse, for which these things, nevertheless, every Lipschitz function is differentiable almost everywhere? And the say loose answer, I'm going to go in more details this after the break, is the theorem. So let me, well, maybe I shouldn't call it yet, but it's theorem. Okay, theorem of Alberti and Marchese, which is extremely loosely stated, so they will apologize me for that, hopefully, is that the existence, and I will give you more details later on, just after the coffee break, about the theorem. So the existence of a measure satisfying the converse of Rademacher theorem is okay, of a singular measure is equivalent to existence of a singular measure mu. Okay, I'm a bit cheating here, but so vector valued. So here, when I talk about converse of Rademacher theorem, I'm talking about positive, classical positive measures. But nevertheless, starting from a measure like this, you can build, and actually, again, it's equivalent. You can build a vector valued measure mu, which is a measure with, actually, it's more than, it's a matrix valued measure. So it's, well, let me write it different. It's the same thing when we use. So it's equivalent to the existence of d singular measures mu1, mu d. So d singular vector valued measures. Vector valued measures mu1, mu d, which are all measures from, say, omega into some rd, such that the divergence of mu I is equal to 0 for all 1 to d. And the second thing is that if you look to the span of the direction of these measures, okay, for each one of these measures, these are vector valued measures, so you can take their polar direction. So this gives you a collection of d vectors. Well, then this is equal to rd. So these d vectors are all linearly independent, at least for mu almost all points. So that's okay. Let me be a bit cheating at most points. But we were on a set of singular on a null set for Lebesgue at most points. Okay, so this is very loosely stated. I'm gonna give you a precise definition of this just after the break. But the point, so the takeaway message here would be that the structure, the existence of measures which satisfy the converse or Rademacher, it's indeed related to the structure of divergence-free measures in a quite surprising way, and it's again thanks to this beautiful result of Giovanni Alberti and Andrea Marchese. But there is a link, and we are going to exploit this link. And same is for what concerns this theorem of Chigger, which Thomas was mentioning. And actually, this can be also sort of starting point in understanding the theorem of Alberti and Marchese is much more precise, as we're going to see. And in particular, you can also argue, okay, they do not only tell you that what happens for the measure which satisfy Rademacher theorem, but in a sense, they are able to generalize this example here in finding for a measure a good direction along which Lipschitz functions are differentiables and some orthogonal, in a sense, direction along which they are not. And you might ask yourself, what is in general the structure for which I have enough of measures for which I have enough directions of differentiability for Lipschitz functions, and so on and so forth. So you see, if you look to this example, you should expect, so in the tangent direction, every Lipschitz function is differentiable, basically because in the tangent direction, you are in the RL situation. And in the orthogonal direction, no Lipschitz function is differentiable. So you might expect that this is what characterizes the typical L-dimensional measures. So this is not completely true, but it's true for some part of the measure. So in a sense, and this is a combination of the work of Giovanni and Andrea with something we did with Philip and other authors. Okay, and I try to mention this at least along the week. I hope I will be able to. Okay, so I think it's the moment for the break.